Hi guys, how are you? I hope you are doing well. So today I'm going to talk about section 14.1 and 14.2, that's functions of several variables and limits and continuity. So first, let me just remind you what's a function of single variable. So when I say a function of single variable, it means a function of only one variable. So for example, you use f of x is equal to x squared. So here I have only one variable, which is x, right? Only one variable. Okay. But then, so now let's say you want to graph f of x. So if you want to graph f of x, well, then you're going to need another axis, right? So you have the variable x, but then you want to graph f of x, you're going to need another axis, which is the y-axis, right? So y is going to be equal to the f of x. So here's my x-axis, okay? And then you're going to need another axis, which is the y-axis. So the y-axis, that will be the y will be the graph of f of x. So for example, you say f of 1, f of 1 is 1 squared, so that's equal to 1. So for example, so here is x equal to 1, right? So what you do, so it means if f of 1 is equal to 1, it means the height corresponding to the point 1 is equal to 1. So here, the height would be 1 here. So here's 1 here. So I get this point here. So for example, you say, so let's say f of 2. F of 2, of course, is 2 squared, which is 4. So if you have 2, so here's 2, right? This is, let's say, 2. So the image of 2 is 4. So it means that the height here, y, the height y is 4, etc. So you see each point, to each x, you associate its image, which is going to be like the height, right? So the image of 1 is 1, so the height here is 1, right? The image of 2 is 4, so the height is 4. That's equal to the y, right? And of course, so then you can join all these points and you get your the graph of the function f, okay? Now, let's say we have more than one variable. So that will be a function of several variables. So let's say, for example, let's say instead of, so now we're gonna have several variables. So let's say you have f of x, y equal to, let's say xy plus y squared, okay? So now I have not only one variable x, but I have two variables. I have x and y, so two variables. Okay, and if you say, what's f of, let's say, 1, 2? So if you want to compute f of 1, 2, then it means your x is equal to 1 and your y is equal to 2. So here my x is 1 and my y is 2. So that will be equal to, so your x is 1 and your y is 2 plus y squared, my y is 2, so that's 2 squared. So that's equal to 6. Or let's say you want to compute f of negative 1, positive 3. So my x again, now my x is negative 1, sorry, and y is 3. So that's negative 1 times 3 plus y squared, y is 3, so that's 3 squared. So that's a negative 3 plus 9 equal, of course, a positive 6. Now, so this is a function of two variables. Of course, you can have more than two variables. You can have three. So let's say f of x, y, z equal to, I don't know, x, y, z plus exponential of x, y plus y, z squared. Okay, so you can have more than one. You can have three variables, or more than three variables. You can have four, f of x, y, z, t, for example. So let's say that's x squared, y squared, plus z squared, t squared, okay, etc., etc. So you can have, of course, more than 4 variables, okay? Now, let's just try to graph functions of two variables. So let's say this is you have a function f of x, y, okay, and let's say f of xy equal to xy squared plus, let's say, y. Okay. So now I have two variables, right? So I have two variables, so I'm gonna need first two axes. So I'm gonna need the x-axis. Remember, the goal now is try to graph this function f, right? So I'm gonna need the x-axis, and then of course I'm gonna need the y-axis. That's my two variables. Okay. But then if you wanna graph f of xy, you're gonna need a third axis. So I'm gonna need the z-axis. Okay. Remember, a function of single variable. So for example, f of x equal to x squared, right? I have only one variable, right? Which is x. So I have my x-axis. But then if you want to graph f of x, you're going to need another axis, the height. That will be like the height, right? So I'm going to need another axis, which is the y-axis. Now, if you have two variables, so I have two axes, x and y, but if you want to graph f of x, you're going to need a third axis, which is the z-axis, and that will be the height. So here's my z-axis. That will be like the height of the function f. Okay, now let's try to graph this function f. So what you do is, you take a couple, let's just take a couple of points here. Let's try to plot a couple of points. So for example, you say, let's say, what's f of 1, 1? Well, f of 1, 1 is 1 times 1 squared plus 1. X is 1, y is 1, so that will be equal to 2. What will be f of, let's say, 0, 1? So f of 0, 1, that's 0 times 1 squared plus 1, that's equal to 1. Okay, f of negative 1, positive 1. So that's negative 1 times 1 squared plus 1, so that will be equal to 0. F of, let's say, 2, 1. So that's 2 times 1 squared plus 1, so that will be equal to 3, right? Now, I'm going to plot these points. How do we plot these points? Well, so first, f of 1, 1 is equal to 2. So what I'm saying here is that if x is equal to 1 and y is equal to 1, so where is the point 1, 1 here? 1, 1, here's my point 1, 1 here. Let's say this is 1, 2, 3, this is 1, 2, 3. So here, this is the point 1, 1, right? And what I'm saying is f of 1, 1 is equal to 2, so the height, z, the image is 2, so the height would be equal to 2. So here's my point, and the image of this point is 2. So let's see if this is z here, 1, 2, 3. So what I'm saying is the image of this point is 2. So here's f of 1, 1. This is f of 1, 1. Okay. Let's take another point, f of 2, 1. So f of 2, 1 is 3. So where is 2, 1 first? Here's 2, 1. Here's 2, 1, right? And the image is f of 2, 1 is 3. So the height would be 3, right? So here's 3 here. So this is, f of 2, 1. Okay, so here's f of 2, 1. This is f of 1, 1. Right? Etc., etc. So the thing, guys, is that, of course, x and y, so here's your, so, you have this whole plane, the xy plane. So you have all these points, and to each point, you associate its image by the function f. So let's say this point here, it goes here. Its height is here. Let's say this point here, it goes here. Okay? So imagine to each point, you associate, its image, its height. Okay? And so you're going to have, so the image, it won't be, it's not just it's not just like a curve, but it's gonna be like it's gonna be a surface. It's gonna be a two-dimensional space. So it's gonna be something like this. Okay, so that will be f of x, y. So the collection of all these points here, all the images by f. So it's gonna be a two-dimensional space. Okay, so it's not one-dimensional; it's two-dimensional space. I mean, if you compare it to the case of function of single variable, you see here single variable, so you have only one variable, which is x, but then the image, it's a curve, right? So the image is one-dimensional because it's like you take the x-axis, and then the image is like you twisted a little bit the x-axis, right? You twisted your number line. Okay, here for two variables. So what you do, you take you take your xy plane. This is your xy plane. Okay, and the image is gonna be it's not as I said, it's not a curve, but it's gonna be some sort of twisted plane. So it's gonna be sort of surface. So it's gonna be a surface. So here's the image here. Okay. So again, guys, you need to understand this difference here between the graphs. So the graph of a single variable. So if you have one variable, the image is gonna be just like one, a curve. So it's like your x-axis, but it's kind of twisted, right? In case of two variables. So the two variables, it means you have the whole plane, xy plane. So you have all these points here. And the image is gonna be something like which is a surface, so it's gonna be a two-dimensional space. So this is the image here. So that's like the height here, right? So to each point here, so here is gonna be this. This is the image here. That's the graph. This is the graph of f of x. So this whole blue region here, that's the graph of f of x. Okay. Now, I'm going to talk about continuity of limits and continuity of a function of several variables. So I'm gonna just focus on the case of a function of two variables. Okay. So let's start with limits of a function of two variables, f of xy. Okay. So let me just first remind you. So if you have a function of single variable, let's say f of x is equal to, x squared, for example. So this is my f of x is equal to y. You have a function of single variable, okay? So, so what will be the limit here? So let's say here f of x is equal to x squared. So here's my x-axis. Okay. And let's say a is equal to, let's say 1. So what's the limit of f of x when x approaches 1? Here, x squared. So here's my, here's x squared, right? This is the graph of x squared. Okay, and here, let's say this is 1 here. Okay, and of course f of 1 is gonna be 1 here. So 1 here, okay. F of 1 is 1 squared. So limit here, it just, so this is limit, x goes to 1 of x squared. So all we have to do is just, first, what we have to do is to replace x by 1. So if we replace x by 1, of course, that's 1 squared. It's equal to 1. So this limit exists because, remember, limit of f of x exists if limit of f of x exists when x approaches a. Let's say if limit of f of x when x approaches a from the left is equal to the limit of f of x when x approaches a from the right, is so that will be equal to So that will be equal to your limit here, equal to the limit. Okay. So what I'm saying here, limit exists if you know, there's let's say this. So a is equal to 1, right? So let's say here's my a. This is my a. A is equal to 1, right? So there are two. There are two ways to approach a. You can approach a from the left, and you can approach a from the right. So there are two ways, only two ways to approach a, from the left and from the right. And what we are saying for a function of single variable, we say that the limit exists when x approaches a if the limit from the left is equal to the limit from the right. Okay. So it means that here from the left, when you approach a from the left, this is the same as approaching a from the right. So if the limit from the left coincides with the limit from the right, then the limit would exist, right? And that's again because here of single variable, in the case of function of single variable, there are only two ways to approach the point A. Okay. Now, in case of a function of two variables, so of f of x of f of xy. So f of xy, we're gonna need x-axis, we're gonna need the y-axis, but also we're gonna need the z-axis. Okay. Now let's say the graph of f of x is this one here. So this is, let's say this is this whole blue region. That's f of x. That's the graph of f of x. So this is f of xy. Okay. Now let's take a point. So here, a single variable, if you take a point x, so here I took a equal to 1, okay, because it's just a one variable, so we take just one value, right? Now we have xy, we have two variables, so I'm gonna take a point. So when I say a point, so I'm gonna need x and y. So let's say you take the point 1, 2. So here's 1, this is 2 here. So this is the point 1, 2, right? Now, what's the image of f1, 2? So this is here. So the height, let's say this is the image of 1, 2. So this is f of 1, 2 here. The height of this point, that's the image of 1, 2, right? Now, how many ways can we approach this point 1, 2? Well, the thing is, there are infinite number of ways to approach 1, 2. So we can approach 1, 2 from, you can approach 1, 2, let's say from here from the left, from the right, or from the diagonal. Okay, from the diagonal here. Or from the top here, etc. Or you can just take some. It doesn't have to be like a straight straight line. It could be like just something which is like a parabola or a curve, some curve here. So there are different ways, to approach this point, right? And so if you approach this point here from the right, so you're gonna get this thing here. You approach the point from the left, you get this thing here, or you approach it from the diagonal, you get this thing here, or you approach just along some curve here. Okay, so you can just approach the point along, it could be any path actually. It could be any curve, right? It doesn't have to be like straight line. Okay, so now the thing is, because there are infinite number of ways to approach the point, then the limit. So if f of xy approaches L1, okay, approaches L1 as xy approaches, let's say, point AB along path, some path C1, and f of xy approaches L2, another approaches L2 as xy approaches AB along another path, let's say path C2, okay, where the two limits L1 and L2 are different, then the limit of f of xy when xy approaches AB, then this limit here do not exist. Okay, so what I'm saying, guys, is that again you have, here's my x, here's my y, this is my height z, and this is my function f here. Okay, this is my function f of xy. So this is f of xy. Okay, so you take a point AB. So here's my point AB. This is AB. And here so what you do, you approach AB, this point AB, along some path C1. Again, it could be from the right, from the left, or it could be along any, any path. It doesn't have to be like a straight line. It could be like this path here. You're approaching AB along this path here. Okay, so this is my path C1. And let's say I approach AB. This is again my point AB. Along another path, let's say here, this path here, this is another path, C2, okay? Now, the image, so here, so this is the image of AB, okay? This is f of AB. So what I'm saying, guys, is that in order for this limit to exist, so if you want to limit of f of xy when xy approaches AB, if you want this limit to exist, then for any, you take a random two paths, let's say C1 and C2, and then the limit of f of xy. So here you're approaching, this is my f of, here this is my f of xy approaching AB along C1. So this is f of C1, let's say, and here this is C2, the image of C2, f of C2. Okay, so you need to, so if the two limits here coincide along this two paths C1 and C1 and C2, then the limit exists. Okay, so but again, the paths C1 and and C2, they are just random paths. Okay, they could be any path. Okay, so the limit of f of xy when y approaches AB exists if the limit of xy along path C1 is the same as the limit of f of xy along C2 for any paths C1, C2 approaching the point AB. So what I'm saying, guys, in case of one variable, there are only two ways to approach A, right? Either from the left or from the right. And in order for the limit to exist, you need the limit from the left to be equal to the limit from the right. Now, what I am saying is, in case of two variables, okay, there are infinite ways to approach. There are different paths, infinite number of paths to approach AB, right? And in order for the limit to exist, you need the limit to be the same for any path approaching AB, okay? Now, in practice, how do we compute, how do we find the limit? Well, for example, so let's do a couple of examples here. Let's say you want to find limit or you have to prove that the limit do not exist. Okay. So first example, let's say we want to compute the limit x, y approaching 0, 0 of x squared plus y plus 1 over, let's say, y squared plus 1. Okay, so what will be the limit here? So in practice, what we do is, the first step is always just replace x by 0 and y by 0. Just always replace x, y by AB. Okay, so here if you replace x by 0, so here x, y approaching 0, 0, it means that x goes to 0 and y goes to 0. Okay, so if you replace this x here by 0, y by 0, here's another y here by 0, so what we get, 0 squared plus 0 plus 1 over 0 squared plus 1, so that's equal to 1 over 1, so that's equal to 1. So the limit exists and it's equal to 1. The limit exists and it's equal to 1. Okay. Now, let's take another example. Okay, example 2. Now, what about limit, again, x, y approaching the origin again, the 0, 0. And now let's say you have xy over x squared plus y squared. So if you just replace x and y by 0, x by 0 and y by 0, so we're going to have 0 times 0 over 0 squared plus 0 squared. So that's 0 over 0. And of course, 0 over 0 is indeterminate. So this is indeterminate. Okay, so 0 over 0 is indeterminate. So how do we compute the limit in this case? Well, so here's, again, here's my x, here's my y, and here's my point 0, 0, right? This is my 0, 0 here. So what I'm going to do, I'm going to try to see what happens if you approach, for example, the 0, 0 along the x-axis. So I'm going to approach the 0, 0 along the x-axis, so from here. Okay. So along the x-axis, if you approach the point 0, 0 along the x-axis, so let's see what happens to the limit. So along x-axis, along the path So when you say x-axis, it means y is equal to 0, right? So along the x-axis, y is equal to 0. So then the limit of x, y going to 0, 0 of x, y over x squared plus y squared is going to be equal to, so the x-axis, it means that y is 0, right? So here, I know that y is 0 because that's along x-axis. So I'm going to just replace y by 0. So if you replace y by 0, let's see what happens. So that will be equal to limit, so x goes to 0. You know that y is equal to 0 anyway. Okay, so limit x equal to 0. So x times y is 0. So time is 0 over x squared or plus y is 0, right? So we know that because, again, we are approaching the 0, 0 along the x-axis. So this is here along the x-axis. You know that the y is equal to 0. So plus 0 squared. So that's limit x goes to 0. So here x times 0 is 0 over x squared in the bottom. So that's equal to 0. So here the limit is 0. So what I am saying is that if you approach the point 0, 0 along the x-axis, along this axis here, limit is going to be 0. So let's take another different path. So let's approach the 0, 0 along the y-axis instead of the x-axis. So let's see what happens along the y-axis. So along y-axis, so that will be this axis here, right? This is along, I'm going to approach this point here along this axis. Okay, along the y-axis. And the y-axis, I know that the y-axis, it means that x is equal to 0. So here now, x is 0. You know that x is 0, right? So then your limit becomes, so you have, limit x, y going to 0, 0 of x, y over x squared plus y squared. You know that your x is 0. So that's 0. So that's the limit. X is equal to 0 anyway. Now, so I'm going to keep y because I don't know the values of y vary, right? So that's limit y goes to 0. X is 0. So 0 times y over x squared. X squared is just 0. X is 0. So that's 0 squared plus y squared. Again, that will be limit y going to 0. 0 times y is 0 over y squared, and 0 over y squared is equal to 0. So this is the limit when you approach 0, 0 along the y-axis. Okay. Now, let's take a third path. So I'm going to approach now the 0, 0 along the line x, along the diagonal. So along the line x equal to y. So I'm going to approach this point here along the diagonal here. So this is my diagonal. This is x is equal to y, right? So along, now, let's see what happens if I approach the 0, 0 along the line x is equal to y. So we have limit x, y approaching 0, 0 of x, y over x squared plus y squared. So now my x is equal to y. Right, so now x goes to 0, y goes to 0. Anyway, x is equal to y, so it means that's just, x goes to 0. Okay. Because y goes to 0, because y is equal to x, it means that x goes to 0. So we have just, let's say, a limit when x approaching 0 of what? So x times y, this y here is equal to x. Y is equal to x along the diagonal. So that's another x here over x squared plus y here is equal to x, so that's another x. So there'll be x squared. So that's equal limit x goes to 0 of x squared over x squared plus x squared. That's 2x squared. So x squared cancel out. So then the limit is equal to half. So you see here, if you approach 0, 0 along the diagonal here, x equal to y, the limit, it's not 0, the limit is half. So you get a different limit, right? When you approach 0, 0 along the x-axis, we got 0. That's first limit. When you approach along y-axis, we got 0. But when you approach along the diagonal x equals to y, we got half. So that's a different limit. So if you get different limit, it's like, so you're taking two different paths and you get two different limits, then it means that the limit do not exist. So the limit does not exist. Because f of x, y goes to, let's say, 0 as x, y approaches 0, 0 along, let's say, the x-axis, and f of x, y approaches half as x, y approaches 0, 0 along the diagonal x equals to y. So I got two different limits, right? So then the limit do not exist. Okay. Let's do another example, example number 3. Example 3. Okay, so now let's say let's compute the limit x, y, again going to 0, 0. But then now let's say you have 2xy squared over x squared plus y to the power 4. So if you use, let's say, x-axis along the x-axis, so then y equal to 0. So along the x-axis, the limit, so limit of x, y going to 0, 0, we said it's 2x y squared, x squared plus y to the 4. So here we said x-axis, so y is 0. So here y is 0. So we don't, y is fixed. So that's the limit x equal to 0. My y fixed. So in the top is going to be 0 over x squared plus 0. So it's going to be 0. Along, let's say now y-axis. Along y-axis, so x, y going to 0, 0 of 2x y squared, x squared plus y to the 4. Again, it's gonna be just 0 over. So here x is 0, right? So it'll be 0 over y to the 4. So it's gonna be 0. So that's another 0. So now let's try the diagonal x equals to y. So x equals to y, then limit xy going to 0, 0 of 2x y squared over x squared plus y to the 4. So x is equal to y, so then you're going to just have x goes to 0, because y going to 0 means is the same as x goes to 0 if x is equal to y. So it's going to be 2x x squared over x squared plus x to the 4. Right, so that's equal limit x going to 0. So it's 2x cubed over x squared plus x to the 4. So it's 0 over 0, but you can just apply, if you want, you can apply Hopital's rule. So here Hopital's rule, for example. Okay, so if you apply Hopital's rule a couple of times, so it's basically limit x goes to 0 of 2 over x. So you see that's 2 over 0, so that's infinity. Okay, so you get a different limit here. So then the limit do not exist. Right, because here we got 0, here is 0, but then here we got infinity, so then the limit do not exist. Etc. So anyway, so sometimes, so let's do a last example here, example 4. Sometimes a diagonal doesn't work. So for example, let's say limit xy goes to 0. So xy going to 0, so x minus y, let's say, over, let's say, again, x squared plus y squared. Okay, so along x-axis, that means that y is 0. So we're going to be limit x going to 0. So y is 0, so it's going to be x here over x squared. Okay, so here you will get 1 over 0. So this is limit x going to 0 of 1 over x, so 1 over 0. So that's infinity, for example. Along x-axis, you don't get 0, you got infinity. If you try, along the diagonal, x equals to y, you get x goes to 0, x is equal to y, so x minus x over x squared plus x squared, so it's going to be 0 over 2x squared, so which is 0. Okay, so anyway, you get different limit. All I'm saying, guys, here is that sometimes, of course, you're going to need more than just the x-axis, the y-axis, the diagonal. So sometimes you're gonna need a different. You're gonna need more than just 2 or 3 or 4 paths. Okay, you never know how it works. So in general, what we can do, if you have, if you have some limit to compute or some limit to prove that it doesn't exist, what we can do is we can use the polar coordinates. Okay, because sometimes you cannot just you have to try all these different paths. Okay, and sometimes you try, I don't know, let's say 5 paths and you get the same line. So you need to try another path, etc., and you get always the same limit for any path you take. Okay, but if you try five paths, it doesn't mean that the 6th path you're gonna get the same limit. It could be different, or it could be the same limit. So in order for a limit to exist, you need that the limit to be the same for any path, and you cannot just try all the possible paths because there are infinite number of paths, right? So in general, what we can do is we can use polar coordinates. So polar coordinates, you just replace x by r cosine of theta and y equal to r sine of theta. So r is like a radius, and theta, that's the angle. Okay, So what I'm saying is, here I have variables x, y. So you can, instead of using x, y, you can use the variable r theta, okay? Where r is the radius and theta is the angle. So for example, if you have, because if you have a point here, well, there is a unique r. So the r would be, the distance from the origin, that's the r. And the angle theta, let's say, would be, this is the angle theta here. So for any point, there is a unique r and theta, except actually the origin, okay? So we can use the polar coordinates. So how does it work, the polar coordinates? So for example, let's say you want to compute limit x, y going to 0, 0 of x squared y over x squared plus y squared. So here, if you try x-axis, right, y equal to 0, you're gonna have y equal to 0, so it's gonna have 0 over x squared, so it's gonna be 0. If you try the y-axis, that's when x is 0. So if x is 0, it's going to be 0 over y squared, you're going to have 0. If you try the x diagonal, x equal to y, so that will be limit x, let's say, goes to 0, so it's going to be x cubed over 2x squared, right? So that's limit x goes to 0, so it's going to be x over 2, which is equal to 0 over 2, which is 0. Okay, so you get the same limit here. But so if you get the same limit for x, y-axis, and the diagonal x equal to y, it doesn't mean that, for a different path, let's say, I don't know, some weird path, you would get the same limit. It could be, you can get a different limit, okay? So this doesn't prove, So it doesn't prove that the limit exists. Again, because in order for the limit to exist, you need to get always the same limit. But here, for any path, approaching the point for any path, right? But here we just tried the 3 different paths, okay? But for the 4th path, it could get a different limit. You never know, okay? So in order for the limit to exist, you need to prove that the limit is always the same for any path, okay? So how do you prove that the limit is the same for any path? Because here you cannot just, there are an infinite number of paths, so you cannot just, try all the possible paths. That's impossible. So what we do here is use a polar coordinates. So I'm going to change the variables, x, y. So my x is, x is r cosine of theta. Y is r of sine of theta. So when xy approaches 0, so xy approaches 0, it means that r approaches 0. So if xy approaches 0, means that r approaches 0. Because if basically you just replace r by 0, then x would be 0, right? And if you replace r by 0 here, y is going to be 0. So if saying that xy approaches 0, it means that the radius r goes to 0. So what I'm going to do, I'm going to start with, so limit xy here going to 0 of x squared y over x squared plus y squared. I'm going to change coordinates, so r is cosine of theta. X is r cosine of theta. So x is r cosine of theta, and y is r sine of theta. So as I said, y approaching 0 means that r approaches 0. So this is the limit r approaches 0. x squared, so that's r cosine of theta squared, times y is r sine of theta, over r cosine of theta, which is x squared, plus y, which is r sine of theta, that's another square. So that will be equal to limit r goes to 0. So the top we have r squared times r, so that's r cubed cosine theta sine of theta, right? That's the top. In the bottom, so we have r squared cosine squared of theta plus r squared sine squared of theta. So in the bottom here, you can factor out r squared, so that's r cubed. Again, limit, sorry. So limit r goes to 0, so we have r cubed cosine of theta sine of theta. And in the bottom, we can factor out r squared, so r squared cosine square of theta plus sine square of theta. Of course, cosine square plus sine square, so this is equal to 1, right? So that's just equal to limit r goes to 0. So we have r cubed cosine theta sine of theta over r squared. So r cubed over r squared, so it cancel out, it's just r. So here it's going to be just r. So this is limit r going to 0 of r cosine of theta sine of theta. So what will be this limit? R goes to 0. So you just replace r by 0. So r here is just 0. And here, theta and cosine of theta is just a number. It could be any number between -1 and +1, of course. Okay, but if you multiply a number by 0, of course, it would be 0. So this is 0 times cosine of theta times sine of theta. It doesn't really matter what's theta here because you're going to multiply by 0 anyway, so you get 0. So here what I am saying is, you change the variable, use the polar coordinates, so you get limit which is equal to 0, and this limit here is 0, so the limit is 0 for, it doesn't really matter the path here. The limit is 0 for any path. Okay. I didn't pick a specific path here, right? My x and y could be the path could be any path here, and the limit would be still equal to 0, right? So here the limit exists and it's equal to 0. So the limit exists. And so limit x, y going to 0 of x squared y over x squared plus y squared, that's equal to 0. Example number 2, let's see a case where the limit do not exist using the polar coordinate. Example number 2. So now let's say xy going to 0, 0 again, and let's say you have xy over x squared plus y squared. So let's use the polar coordinates and see what happens here. Polar coordinates. So just replace x by r cosine and y by r sine. So that will be limit r going to 0, right? Because if xy approaches the origin, it means that the radius goes to 0. So r goes to 0. So here it's r cosine times r sine over, again, r cosine square plus r sine square. Okay, so that will be limit r going to 0. So r times r here, this r here times this r, so that will be r squared. So it's going to be r squared cosine of theta sine of theta, and in the bottom again, you're going to be r squared, so you factor out the r squared, so r squared cosine square plus r squared sine square. So you factor out, the r squared, so that will be limit r going to 0, so it's r squared in the top, cosine of theta sine of theta over r squared cosine square plus sine square. So you see here, of course, cosine squared plus sine squared, this is equal to 1. So that will be limit r going to 0. So r squared cosine of theta sine of theta over r squared. So then r squared cancel out, right? This r squared here cancel out. So it's just, so the limit here is equal to cosine of theta sine of theta. Now, r going to 0, right? Again, this is limit r goes to 0 of cosine theta of sine theta. Now, this limit here, you see it's equal, so it's equal to cosine of theta. There is r equal to 0, but there is no r anyway, so it's just cosine of theta sine of theta. So cosine of theta sine of theta depends. This depends on theta, right? Depends on theta. So for example, if theta is equal to 0, so then the limit would be equal to what? So cosine of 0, sine of 0, right? Cosine of 0 is 1 times 0 is 0. But let's say theta is, pi over 4. Then the limit would be cosine of pi over 4 times sine of pi over 4. So that's square root of 2 over 2 times square root of 2 over 2. So that's 2 over 4. So that's half. So you see here, the limit depends on the angle theta. So if theta is 0, you get 0. If theta pi over 4, you get 1/2. If theta is pi over 6, you get another value, right? So the limit here depends on theta. So it depends in some sense on the path. So the limit depends on the path or in theta. So it means that the limit, does not exist, because here it depends on theta. You see the difference between the previous example. In the previous example, we got r cosine of theta sine of theta. So because r goes to 0, so you replace r by 0. 0 times cosine times sine, it's always 0. It doesn't really matter what's theta, right? Here, there's no r here. So we got the limit is cosine of theta sine of theta, and this depends on the limit on the angle theta. So if you pick a different theta, you get different limit, so then the limit do not exist. Okay. So this is for the limit. So in general, you see, guys, the best way actually to see whether the limit exists or not, or if the limit exists or doesn't exist, is to use the polar coordinates instead of trying different paths. Of course, you can try different paths, but I think so. The best way would be just to use the polar coordinates. Now, now we can define the continuity of a function. So, it's like for a function of single variable. So a function f. So f is continuous at the point AB if the limit of f of x when xy goes to AB or approaches AB is equal to f of AB. Okay, so this means for a function of single variable, it means there is no jump or hole at AB. There's no jump or hole at AB. Okay. So let's do an example here. So let's say f of x, y is equal to, so the value of f of x, y, the value of f is defined by, so it's going to be x cubed plus y to the 4 over x squared plus y squared if x, y is different from 0, 0, from the origin, okay? And it's going to be 0 if x, y is equal to the origin, okay? So here, what I'm saying, guys, is that what will be f of 0, 0? F of 0, 0, if x, y is equal to 0, 0 is equal to the origin, then this is the image. So f of 0, 0 is 0. We know that f of 0, 0 is equal to 0. Now the question is f continuous at 0, 0. Well, f is continuous at 0, 0. So by definition, if the limit of xy going to 0, 0 or approaching 0, 0 of f of xy is equal to f of 0, 0, which is 0. So if this limit here, if the limit of f of xy when xy approaches the origin, is equal to f of 0, 0, then the f would be continuous. So we need to, compute the limit. So what's the limit of f of xy when xy approach the origin? Okay, so we need to compute the limit x, y going to 0, 0 of f of xy. So what's this? Well, this is limit xy going to 0, 0 of... So when xy approaches 0, 0, so what's the value of fxy? Well, if xy approaches 0, 0, it means that actually xy are not equal to 0, 0. They're very close to 0, 0, but they are not equal to 0, 0. So that means that we have to use this function here, this expression of the function f. That's because when xy approaches 0, the origin, it means that they are not actually equal to the origin. They are close to the origin. So if they are not equal to the origin, if xy are not 0, then this is my function f. So here we're going to have x cubed plus y to the 4 over x squared plus y squared. So I need to compute this limit, and as I said, the best way actually to compute this kind of limit is to use polar coordinates. So x is r cosine and y is r sine. So that's the limit. So xy approach the origin, it means that the radius approaches 0. So then r goes to 0. So we're going to have r cosine theta cube plus r sine theta 4 over r cosine theta square plus r sine of theta square. So that's the limit, r going to 0. So we're going to have r cube, r to the 4. So here's this r cube cosine cube of theta plus r to the 4 sine to the 4 of theta over r square cosine square plus r square sine square. So that would be equal to, well, here in the top you can factor out r cube, right? This is r cube, is r to the 4, so we can factor out r cube. So this is limit r goes to 0, so we have r cube in the top. So we have cosine cube of theta plus the r to the 4. So if you factor out r cube, that will be just r sine to the 4 theta over, and in the bottom you can just factor out the r square. So cosine square plus sine square, that will be 1. So it's just r square here. So here's r square. So r square cancel out with so cancel out. So it's just limit r going to 0 of cosine cube of theta. So we have r cube over r square, so that will be r. So that's r cosine cube plus r sine to the 4 theta. So r goes to 0. Just replace r by 0. So here r by 0. So that will be here 0 times this whole thing. So 0 times cosine cube theta plus 0 times sine to the 4 theta. So it's going to be equal to 0. So the limit xy approaching the origin of f of xy is equal to 0. And that's, but 0, it's f of 0, 0, right? So then f is continuous because the limit of f of x is equal when x and y approach the origin. is the same as f of 0, 0. So then f is continuous at 0, 0. Okay. Anyway, guys, I guess I'm gonna stop here. You can find more examples in the lecture notes. And again, if you have any question, just send me an email. Okay, thank you. See you next time.